I'm Cathie Wells. I was a teacher for 21 years, and then I decided to go back to university because I was so inspired by all the ideas my sixth formers had on what they wanted to study at university. So I decided to go back and do some more maths, and I joined the Centre for Doctoral Training for Mathematics of Planet Earth, and that was a joint venture between Imperial College London and the University of Reading, and it meant that I could use my mathematics to try and solve real world problems. So I did a year-long MRes and then my project for the 3 years for the PhD. And I was able to work with people from both the mathematics department and the meteorological department, because obviously Reading has that really unique link between the two. And that led me to meeting Professor Paul Williams, whose idea it was to start looking at the transatlantic flights and whether we could reduce emissions. And the idea was really to try and get to some kind of win-win approach where airlines would be so delighted by the savings they would be able to make, not just in emissions but also in fuel, that they'd be really likely to take on board what we were saying. And the project that you sort of gave the award for, that research was the proof of concept, really the first step in showing that time minimal routes were much better than trying to use the organised track structure, which has been used for the last 60 years.
Thank you. So I think, tell us a little bit about your project, reducing craft emissions by improving transatlantic flight routes and the origin of that research. But I think you've already done that. So.
That's okay. But yeah, the project itself, we were really worried about the effect that commercial aviation is having on the world, because at the moment commercial aviation emits only just less carbon dioxide than the whole of Japan, and so something has to be done. Most of the sort of ideas that are out there are quite high risk and expensive and long term. So yes, aeroplanes can be redesigned and fuel can be redesigned, but that's not necessarily going to be something that can happen tomorrow. However, what we did see was that there's a change in the way that aircraft are being tracked. So there's now a ring of low Earth orbit satellites. And that means instead of having really poor situational awareness across the North Atlantic, we've now got a situation where 100% coverage is possible. So that means that aircraft can start to fly on routes that are less structured than they have been in the past. And that meant it was the perfect time to start trying to come up with an idea that would be low cost, low risk, and would also be operational almost immediately. What we wanted to do was really prove that by optimizing the routes, in the first instance, we used time minimal optimization, and we could show that the distance that the aeroplanes flew relative to the air around them was a lot less than the distance they flew if they were going along one of the organized track structure routes. The idea behind that was to show that we need to be more flexible in the way we plan aircraft trajectories, because in the first instance, the less time they spend in the air, the less fuel they're burning. Later on, we actually moved into looking at fuel minimization and found that we could get even more savings with the carbon dioxide emissions by looking at fuel minimization as well.
Thank you. Now, I hope you don't mind, but I'm going to go off script because I'm really interested in your project. So I'm going to ask you two questions about the project itself. So the first question is, clearly you focused on North Atlantic air travel at this point. Does your work have applicability to other parts of the globe and to other aeroplane routes?
So the key idea with using the North Atlantic is that you've got a really slowly evolving jet stream, and that means it's much easier to predict what the wind fields are going to be like. It's not quite so easy to start predicting across particularly land masses where geographical features are going to change what the winds are like. That means you can't predict in advance so much. You've also got quite a strong, because of the jet stream, you've got quite a strong pattern of where the winds are going to be flowing. And that means that going eastbound, you can really make use of that. Flying westbound, you have to try and avoid it. In other regions, so the same mathematics can be applied to other areas. I looked at some Pacific routes as well, but you're not going to get the same kind of gains because the winds are not following such a solid pattern, if you like.
Understood. Thank you. And the other question that's not on the script is you mentioned in passing talking to airline companies about your work. have you approached airline companies, and how receptive have they been to your findings?
So some people from different groups within aviation have talked to us. I talked with the people who are involved in the ECATS conference, and they're involved mainly with the Single European Sky project. And we also talked to the air navigation service providers, so in this country, NATS, and they were really keen to talk about the work when the first paper came out. So when this first piece of research was published, we did a seminar for them, and they talked to us about the fact that they were wanting to investigate what would happen if they took the track structure away. And they actually tried a few days without the track structure. And then more recently, so from March 2022, they actually took out the structure up to 33,000 feet. And I'm sure that there's more that's going to happen on that front. And I think that's just a first step. And in the future, we'll expect to see that organised track structure being moved away from in quite a strong way, because we're going to be able to move from that organised track method of flying to what we call trajectory-based operations. And that means that every single flight, the trajectory can be created based on the atmospheric conditions that the aircraft is going to meet as it flies across the North Atlantic. So it's a really important time for flights, particularly in that region.
Very, very promising. What does winning Research Project of the Year STEM at the Times Awards in 2022 mean for you and your collaborators?
So for me, it was really exciting to get the recognition that our work was making a big impact and that people were really interested in what we were doing. We already knew when the first paper was published that it was work that was of interest, because we got so many different people from newspapers, scientific magazines, scientific groups wanting to talk to us. And I did some radio interviews and some interviews for the newspapers. But it's really good when you get groups of people from outside of the main media who are really keen on what you're doing and can see that it's making a huge difference. I think with my collaborators, it showed just how useful it is to have a group of supervisors who are drawn from different disciplines. So I was working with my main supervisor, Professor Paul Williams, who's from meteorology, and he had the initial idea, and he talked to someone who works more in the sort of aeronautical engineering sector, so Professor Ian Poll, who'd come up with a new fuel burn formula that he wanted us to maybe make use of in some of the work, which we used in some of the later research. And then we had a couple of mathematicians who are really keen to join us. So we had Professor Nancy Nichols from Reading, who's done a lot of work in optimization in the past. And then from Imperial College London, Dante Calizze, he came on board to look at maybe some of the dynamic programming possibilities. So it showed that by winning the award, it proved that having a really strong group of supervisors from different disciplines makes a big difference to how applicable any research is. I think that's one of the really key parts of this. I think in terms of Reading University, it was really important because it shows just the unique position that Reading University is in to be able to provide mathematics and meteorology together and to combine that with the use of computer modelling. So I think overall it meant a huge amount to me. But also it was really helpful for both the university to get that recognition and for my supervisors, so that they're more likely to get involved in interdisciplinary projects in the future.
That's all very gratifying to hear that it's had such a positive impact on you and your university and your fellow advisors. I go on to the third question. You've given me some hints as to this already when talking about industry response. But let me ask you: are there any updates on this project since you submitted in spring 2022?
Yes, yeah. We started off with time minimal approaches, just so that we could really have a nice comparison between the organised track structure and our time minimal routes. And those were based on the Zermelo equations from the 1930s. And we looked at optimising using Pontryaghin's minimum principle. But from there, we thought it would be really good to start looking at fuel minimal routes, which people hadn't done so much in the past. And that was possible because of Ian Poll's formula that looks at aircraft fuel burn based on physics and dynamics. Previously, there's been a set of data that people have always looked back to when they've talked about aircraft fuel consumption, but we wanted to move away from that to have something that was actually an equation that we were using to look at fuel burn. So we looked at two different parts of research. One was looking at fixed time routes, and then we were seeing what the difference was between just varying the heading angle of the aircraft across their route to try to minimize fuel, or also changing the airspeed. And we were able to prove that it was worth using both of those control variables. So we would actually in future plan in terms of not just the route for the aircraft, but also the airspeed, so that it can make the most of the winds and really fly at the most optimal airspeed at each point. From there, we opened it back up to look at a dynamic programming method, which allowed us to change the airspeed and the heading angle, but at the same time as trying to minimize the fuel, just see what happened when we opened the time up so it was no longer fixed. When we did that, we found that there were huge savings that could be made. So in the initial time minimal work, we looked at just the differences between the planes that flew on particular tracks each day compared to our time minimal routes. And that showed savings of 6.7 million kilograms of carbon dioxide. When we compared instead with our fuel minimal routes and actual flight plans that had come through looking at real data, we were able to show we could save 16.6 million kilograms of carbon dioxide. So that's about a 4.6% reduction in carbon dioxide emissions across flying, if we're flying eastbound, and westbound it's just under the 4% mark. But that's a huge difference for aircraft, considering they're just having to change the speed they're flying at and the direction they're flying in, rather than having to make big technological changes.
What are the tools, systems, or other kinds of support that helped you to conduct your research?
So we were mainly working with the computer coding language of MATLAB for our simulations. We worked from some Zermelo equations, which we then updated to go from a two-dimensional flat map to a three-dimensional, well, a sort of three-dimensional shell. So we were looking at mapping conformally onto a sphere. With that, we were trying to do comparisons with aircraft routes that had actually been flown. We used some data from the NATS tracks telling us each day what the different organized track structures were. But we also, when we got to the third piece of research where we were trying to compare with actual flights, we used some of the flight radar data information from their website. That meant that we would have positions and times for aircraft, and then from there we could model what the ground speeds would be, and then use our data. We used reanalysis wind data and air temperature data, and that was from the NOAA website, and that allowed us to use the same daily averages both for our simulations and for the actual data that we got on flight routes.
So it sounds like some pretty hardcore, heavy-duty equipment or capabilities, I should say. In terms of
there was a lot of memory usage. Yeah, so memory became quite an important part of everything. And at one point I did a bit of work with the Met Office as well. And then we were looking at climate models, global climate models. And at that point, it was a huge amount of data that was being used. I think using the reanalysis data was a bit more manageable because I was able to make use of daily averages and just using the particular tracks I needed rather than having to use a whole global climate model, which would have made it a little bit unwieldy. We also decided on a particular time period to look at. So we looked at from the 1st of December 2019 to the 29th of February 2020, which luckily was just before all the flights got grounded. So it was quite useful that we finished our winter season there.
Let's come on to the fifth question. I think you've touched on this many times throughout, but I'll ask the question anyway. What is the long-term impact, economic, societal, or otherwise, of your project?
I think the most important thing is that we're changing how much carbon dioxide is being pumped into the atmosphere, because it's really important that we're mitigating to try to reduce the whole global warming issues that are already being seen in so many different countries. If we can change the way that aircraft are flown, then it makes flying actually a little bit more sustainable, although clearly there's a lot more that still needs to be done. But the changes in terms of changes in fuel and changes in aircraft design, those will come online in the future. For the moment, it's a case of trying to do the best we can to make flying as sustainable as possible in the short term. And I think the work we've done has really shown that this is a possibility. And the fact that we've discussed with NATS and they've cited our work in their reasons for changing the way that the organised track structure is run, which hadn't been done for the last 60 years. I think that's a really important impact. In the future, I think there's going to be a need to maybe look at other kinds of pollution as well, not just carbon dioxide. So we might be looking at things like trying to avoid supersaturated icy regions where you might create contrails. But I think more research is being done into that at the moment. It would also be really nice to include maybe things like altitude, because we were keeping to fixed altitude flights. I think there's a chance that changing altitude in a plan, it might be a good idea. It might be that you're better to not change the altitude until you need to avoid things like turbulence and supersaturated icy regions. So that's a possibility for future work, but we'd have to see whether it's an important difference or not, because certainly looking at the wind fields, there's not a lot of difference within those cruise altitudes that you could change to. The only real reason for changing the altitude would really be as your fuel burns off, that the aircraft works more efficiently at higher altitudes.
Last question. So what are the next steps for your project?
So the next steps would be probably to change the programming language in order to allow for larger array sizes. And that means we can have some more control variables and some more state variables, because using dynamic programming, we can start to block off certain areas. If we want to avoid turbulence, we can start to maybe use some more probabilistic forecasts rather than what we've used as a deterministic reanalysis set of data. But looking to the future, you wouldn't necessarily know exactly what your wind field would be a priori. So it's quite important that you would be able to use a more probabilistic range of data. That would all be very useful. I think also maybe there's a chance that you could put some artificial intelligence in there. So if you've got lots of different wind fields and temperature fields, and you've got lots of fuel optimal routes, maybe there's a chance to say, okay, let's feed all that in to train a computer that will then say to us, okay, if that's the wind field and that's the temperature field that day, here's the route that we think would be best, without having to go through all of the simulation. So it'll be really interesting to see how that would play out.
Thank you, Cathie. That was wonderful.
Okay.
Really, really interesting as well.